So what I've got here is an audio laser, also known as an ultrasonic parametric speaker. It can transmit sound in a very narrow and directional beam, like a laser beam, and you wouldn't be able to hear it unless it's pointed directly at you.
Guten Tag, my name is Gene and I'm going to show you how to build an audio laser for under 20 bucks. First of all, what is an audio laser? Some call it an audio spotlight or an ultrasonic parametric speaker. The more common name is an audio laser, and it does exactly that. It transmits sound with a laser beam-like focus and precision. First, we all know how a regular speaker works. The sound is not very directional and spreads out very quickly from the speaker. Everyone in the room can hear a speaker playing music. But a parametric speaker is different. Using various techniques and hardware, such as ultrasound transducers and complex modulation schemes, one can focus a beam of sound like a laser and transmit it so that it hits a very specific target while everyone else around doesn't hear a thing. Let's see how this works. First, a brief history on parametric speakers. From the 1960s to the 1980s, research was conducted into generating sound from the nonlinear interaction of ultrasonic waves. However, it was abandoned as non-feasible due to high distortion. Then in 1988, MIT introduced the audio spotlight, which was the first device capable of reproducing speech through the demodulation of high-frequency ultrasound. Finally, today we are able to achieve similar results through the development of faster microcontrollers and cheaper ultrasonic transducers. As far as I've been able to discern, there are two ways of making an audio laser. The first involves using a single ultrasonic array that outputs modulated ultrasound, which when it hits a target, it demodulates back into the audible frequency spectrum according to a complex nonlinear equation. The audio quality of this method is highly dependent upon the modulation method used. The second method involves using two ultrasonic arrays that output modulated ultrasound that interfere with each other. In the region of interference, the waves are constructed in such a way that the constructive and destructive interference produce audible sound. We will be using the first method in this project. Wikipedia gives us a complicated nonlinear equation for calculating the demodulated pressure wave coming from a modulated ultrasonic source. This is not necessary. Keep watching and I'll show you how to avoid the complicated math and get your directional ultrasonic speaker up and running quickly. Now let's take a look at the major functional components of the system. Audio comes in through the line-in microphone jack and then goes through an initial preamp circuit. The amplified audio is then sampled by the microcontroller using an analog to digital converter. The microcontroller then takes the sampled input audio, modulates it on a 40 kilohertz carrier signal using a pulse width modulation scheme. For anyone with experience with Class D amplifiers, the modulation used here should be familiar. Finally, the complementary output is then sent to an H-bridge circuit, which acts as an audio amplifier that drives our array of ultrasonic transducers. Simple. The main component driving the audio input sampling and modulating the signal for the output is the STM32F103 microcontroller. I chose this device because I have several laying around and also because it's cheap and easily obtainable for the hobbyist. The, the microprocessor runs at 72 megahertz, offers a 12-bit analog to digital converter, 7 timers, hardware PWM, and programmable complementary outputs, which provide better inputs to the H-bridge driver in the output stage. The output of the STM32 is a 40 kilohertz PWM signal whose duty cycle is adjusted in software. The 72 megahertz system clock allows for a duty cycle adjustments in increments of 1/72 millionths per second. This allows for 1,800 possible settings for the duty cycle, giving us a little less than around 11 bits of resolution. For comparison, typical CD quality audio is recorded at 16 bits of resolution, so don't expect CD quality sound from this setup. An obvious upgrade would be a faster processor that could dynamically change the PWM duty cycle a lot faster, but I used what I had available. Now I'm going to show you the parts that I used. Many of these parts were chosen because it's just what I had lying around in my parts bin. First, you'll need ultrasonic transducers. I picked these 40 kilohertz transducers because they were cheap and I already had a bunch available from another project. Make sure you get the TCT40-16T and not the R version. The T version is for transmitting. I couldn't find a good data sheet for this transducer, but it does seem to take an input voltage of up to 150 volts peak to peak and has a range of approximately 18 meters or 54 feet. I used 17 of these transducers to make my array. Using more, you'd probably get better range. For those thinking about improvements, this is one area where better transducers would probably improve not only the audio output, but also the directivity. If you use more transducers, higher frequency transducers, or another type of transducer, drop a comment in the comment box below to let me know your results. As I mentioned previously, the microcontroller is the heart of the system, driving both the audio sampling and the modulation of the output signal. Grab an STM32F103 for under $2, or if you use a different processor or feel another processor would work better, drop a comment below and tell me why. The preamp is built from the ubiquitous LM358 audio op-amp. I used this part because I had a bunch of them sitting in my parts drawer. Again, this is another part that could easily be replaced with a better performing solution. There are several op-amps that have much lower noise and higher slew rates than this one. Also, this op-amp is not rail-to-rail, so there's probably some clipping going on, or at least not being able to use the full volume range. A low-noise, rail-to-rail audio op-amp would be a great upgrade here. Let me know in the comments below what your results are with other op-amps for the preamp stage. Finally, the audio amplifier that drives ultrasonic transducer array is the TC4427A, which is basically a MOSFET H-bridge on a chip. Again, not an ideal audio amplifier, but hey, it's what I had lying around in my parts bin, so I used it. Be aware, if you use the TC4427 to drive your transducer array, it has a stated operating voltage that tops out around 18 volts. Many ultrasonic transducers can be driven at a much higher voltage. In fact, the TCT40-16 I am using in this project has a maximum input voltage of 150 volts peak to peak. In order to get more range and more power out of your array, you may decide to use a more powerful audio driver. Let me know in the comments below if you've changed the output driver circuit. The rest of the components should cost you under $2.50. Note, an MT3608 step-up module is optional if you aren't using a LiPo battery or an external power supply to power your circuit. You'll need to build an array of ultrasonic transducers. This is what we will use to drive the circuit in the next slide. And here's the circuit diagram I sketched in KiCad. All the parts from the block diagram are easily identifiable. The code for the STM32 microcontroller is downloadable on GitHub, and the link is in the description below.
It's kind of hard to demonstrate on video because my laptop microphone has trouble picking it up, but it's actually quite loud and audible if I shine it right at me. It's very loud, actually. It's got a range of about 50 to 60 feet, and I've used it to communicate with my neighbor across the street without anyone else hearing. Really fascinating. And it can even be blocked by a piece of paper. And what's really cool about it is I can aim it at something, and whatever it's aimed at, the audio will sound like it's emanating from that object. So I can aim it at the wall behind me. Let's see if you may not be able to hear that on the video, but to me it sounds like the sound is coming from that picture right there. You can aim it at the ceiling, and now to me it sounds like the sound is coming from my ceiling.
Conclusions. We built an ultrasonic directional speaker for under 20 bucks. The sound quality and range are pretty good, but they can be improved. The code and all the circuit diagrams are on GitHub. The link is in the description below. Suggested improvements include a faster microcontroller, a lower noise preamp circuit, a more powerful output amplifier, and more or higher frequency ultrasonic transducers. These improvements will push the cost of the circuit above $20.